For Unit 1, the universe, we are now on our last week, and we're going to talk about the solar system. So, our star is called the sun. There's no other name for it, not like Betelgeuse or Deneb. It is just the sun. Our sun is about 4.6 billion years old, and our sun formed from a nebula, which we talked about last week, a place of gas and dust. So our sun was formed in a solar nebula. And what you have is the sun that starts to collapse, and then most of the material forms our sun, and then there's some leftover material that forms a ring around the sun, and it just starts to orbit around, and eventually all of that dust collects and gas collects to form the different planets that we have. We talked about light years last week. That is to measure distances between stars. But for measuring distance between planets, a light year is way too long. So we have to come up with another length that we want to use. So the length that we use is called an astronomical unit. And so it's based off, because we're Earthlings, we decided this. We decided that 1 astronomical unit is the distance between the Earth and the sun, which is 93 million miles. Now, how does this work in our solar system? Well, let's look at Jupiter. If we looked at Jupiter, how far out is Jupiter from the sun? Well, it's 1, 2, 3, 4, 5.2 astronomical units away from the sun. So it's just a unit of measure in a way we measure distance in our solar system specifically. So our sun, remember, is a yellow main sequence star. Although some say it's a white main sequence star or it's a yellow-white main sequence star. But overall, it is the class for the yellow stars. So it is, we don't know it's already 4.5 billion years old. And when it turns 10 billion, it will expand to a red giant, like we talked about last week. And then it'll form a planetary nebula, give off the gas. And then we'll have a white dwarf left, and eventually maybe a black dwarf. So you can kind of see where we are. We're right here. Notice that in the future, in billions of years from now, our sun will be warming up. So eventually, our planet will not be very habitable anymore. And eventually, the red giant will probably destroy our planet when it becomes a red giant. So that's future. It's nothing to worry about now, because billions of years is a long time. Nothing that us humans can really worry about. So the sun is made out of a plasma, which is ionized gas, and it doesn't really have any true sharp boundaries, but scientists always like to give everything a label and a name, and so we have broken up the sun into different parts. I did want to go back to maybe middle school when we taught, if you learned about heat transfer and how heat can be transferred 3 different ways. Usually conduction, which is the heat is transferred through a solid by direct contact. So this, the handle of this pan is going to be hot because of conduction. Convection is usually about liquid or gas, and the liquid or gas will circle around. So the boiling water is heating up and transferring heat by convection. And then we have radiation. So the reason why you can put your hand down near the fire in the air and hold it out and feel the heat is that heat is radiating away from the flame. So remember that the sun gives off electromagnetic radiation. So that's pretty much how we feel heat here on Earth, is by the radiation coming off of the sun. So let's start with the solar interior. Interior just means the inside. So the very inside right here is the core. That's where nuclear fusion happens. Remember, nuclear fusion is hydrogen plus hydrogen, which makes helium. And when it does that, it gives off lots and lots of energy. That is important for us Earthlings, we depend on this energy that the sun gives off. From the core, that energy is going to travel through a section of the plasma called the radiative zone, which simply means it's transferring the radiation, the energy through that area. And then we'll get to the outside edge of the sun, and this is called the convective zone. As we can see that the gas, the plasma, will be kind of moving around and heating up and circling like it's boiling. So nuclear fusion is a little more complicated than just hydrogen plus hydrogen makes helium. It has many steps. It actually creates different types of hydrogens and heliums before it finally makes the stable form of helium, which is a mass of 4. But the main thing we want to know about is like the fact that the sun is going to give off protons, neutrons, positrons, gamma rays, and neutrinos. Those are all flying away from the sun out into space, and they do hit Earth. Now, the second part of the sun is the outside part, the edge, which we call the photosphere. Photo means light, so it's the part that we see. Now, the photosphere doesn't look just pure orange or pure yellow. It actually is some sort of mix. So when we look at the photosphere with a solar telescope, never stare at the sun, we actually see that it has dark orange and light orange or yellow. So it has it's much more beautiful, I think, and more complex than what we kind of just see as this ball in the sky. So the dark orange, the light orange, those are called granules. And again, this is all because of the convection below and the temperatures. We're talking about 10,000 degrees Fahrenheit. So anything on Earth would pretty much melt on the surface of the sun. The chromosphere is actually the atmosphere. So on the edge, you see all that red gas that's just above the surface of the sun. That is called the chromosphere. And what we do see often with the chromosphere is that the red gas kind of spikes all around, and we call those spicules. But just like the Earth has an atmosphere, a trapped layer of gas, there's a trapped layer of gas around the photosphere of the sun. And then finally, we get to the corona. This is what we usually draw. When we look up in the sky, not directly at the sun, but to the edge of the sun, we do see this bright yellow that all around. And it's why we draw the sun the way we do. We're actually drawing the corona that goes around the sun. So remember, the sun is a star and a star is a sphere. And it is a sphere, but it does have this corona of gas. And so that's what gives it that shape. So again, we have our photosphere, we have the chromosphere, which is the red gas jets, and then we have the light yellow corona around the edge. Now, our sun also has something called sunspots. That's these black dots on the sun. And those black dots are actually much cooler temperature than around. Now, when I say much cooler, 1,500 Kelvin less. So if we went back to this temperature, right? If it's at 6,000 Kelvin minus 1,500, that's 4,500 Kelvin. It's still hot for human beings. Can't land there, can't touch the sun. But it is cooler for the sun. Now, the sun goes through this cycle where every 11 years, there's a bunch of sunspots. And then the sunspots go away, and it's like a perfectly smooth surface. We don't see any dark spots. And then 11 years later, a bunch of dark spots. Now, this affects its activity, which just means what comes out of the sun. So the prominence is sometimes we see that gas will go way out and then come back. And it's because the sun actually has a magnetic field, just like the Earth has a magnetic field. And this loop is really showing you the magnetic field on the sun. Now, look how big it is. Like just this prominence, here's tiny little Earth. It would fit right here as we're looking at the sun. Now, the sun, like I said, gives off those protons and those neutrinos and electrons. That is going to be called the solar wind. It's a stream of protons and electrons, and it just flies out in all directions. In all directions, we're just showing one direction, but in all directions away from the sun is the solar wind. So, in a way, it's windy, but it's not windy like we think, but it is wind out there. Um, and then what we do notice is that the solar wind will increase if we have a solar flare or a CME, and those things cause auroras. So, a solar flare is a little bit extra, right? So, we had just protons and electrons flying away. That's normal every day. But then sometimes when we get a little extra, which is an extra explosive release of energy, and it usually you see this really bright thing happen, and boom, out straight out from there, that's a solar flare. And so it's adding extra ultraviolet light, extra radio waves, extra X-rays are shot out in a straight line from the solar flare. Now, the other thing that can happen is something called a coronal mass ejection, and that actually is corona gas flying away from the sun. So it's supposed to be trapped by the sun, but once in a while, the gas will just like fling out away from the sun to out to the solar system. So it travels over 1,000,000 miles per hour, and so it might take about 3 days to reach Earth. So we can actually usually see. And this cause a little bit more stuff to happen on the Earth. The CME can change our magnetic field a little bit, can affect the power grids on Earth. Now, it has to hit us directly, though. So most of the time, the gas jets just fly out and they don't even come close to us because they are in a different direction. So we have to be right in the path of one of these CMEs to have it affect Earth. So here is just NASA's little video about the difference between a solar flare and a CME. The sun is very dramatic. And this comes from 2 satellites that we have going around the sun and monitoring the sun's activity. All right, so that is our wonderful sun, very active.